The most challenging part of the section on atoms and moles is actually keeping all of the different notations straight. So this is a quick list. Note that there are two different capital N's, a lowercase n, lowercase m, and two different capital M's. So this is really confusing, and especially for those of you who've had chemistry before, I expect that this notation is a little bit different than what you've seen in chemistry. So keep in mind that using a consistent notation will be really helpful in your work. If you need to use a different notation, or if you choose to, at least make it really clear at the beginning of any of your written work what you're doing. So typically, capital N is going to be for number of atoms, and that's going to be a variable. Volume, also a variable. Now, we're not going to frequently work with atomic mass number or the atomic mass or molecular mass of a given compound, but the book is using capital A for atomic mass number and lowercase m to then talk about the atomic mass of a given or molecular mass of a given item. Capital N sub A is what we use for Avogadro's number, and this is basically a constant. And it does actually have units of per mole or 1 over mole. And the book truncates mole to be MOL. So keep in mind that that's not per molecule, that's per mole. We're using lowercase n for number of moles. And the reason why you want to keep this straight is on the equation sheet, when we get to the ideal gas law, there's going to be one equation that involves capital N and one equation that involves lowercase n. So you want to keep track of which one's which, since otherwise you'll be using the wrong equation. The total mass, and I say total mass here, but this is pretty much just normal mass of an object, is m, and then the molar mass of a given substance is going to be capital M sub MOL. And this is like how much does a mole of something weigh, or what is its mass. And again, some of these we won't really come back to, at least not for the topics that I stress in this class, but this is all of your notation. There are two types of density, and this actually is important and something we will come back to a few times. There's mass density, where we use the variable rho, which kind of looks like a funny p, and then there's number density. The book doesn't define a variable to represent number density. Whenever it means number density, it's actually going to write capital N over V. So the idea of number density is just it's how many you have per volume. And the idea is, if you imagine this tennis ball where they're evenly spread out, if we take different volumes of the room, we actually get different numbers of tennis balls. But when you divide the number of tennis balls in that volume by the volume, you get a constant value. So it's proportional. Now, number density is just units of m to the negative 3, which means 1 over cubic meters. So number per cubic meter. Mass density is going to be mass divided by volume, so it's kilograms over cubic meter. So that's the big difference there, but do keep track in a problem as to whether you're told number density or mass density, and if you're asked to calculate something, keep these straight. In general, if I just say density, I mean mass density, but I'll try to be specific when we're in a situation where I could mean either. One final thing that's important from this is to note that some gases are monatomic, meaning that the quote-unquote molecule of that gas is simply a single atom, while other gases are diatomic, meaning that you have two atoms of that gas joined together, which forms your gas molecule. And many common gases are diatomic, and these are, say, like noble gases can be monatomic. The reason this is pointed out is that later we will have some equations that do depend on whether a gas is diatomic or monatomic. This table is not on the equation sheet. So hopefully this is something you can get a sense for, what is diatomic and what is monatomic, if it's not something you're already familiar with.